Thank you so much for having me. And I apologize for my quarantine attire. Today I'll be talking about designing cameras to detect the invisible, computational imaging for adverse conditions. So imaging and vision systems surround us in our daily lives, be that in our personal devices, in health and robotics, or in autonomous vehicles of the future. So to build vision and control systems for these very diverse applications, they must handle harsh and oftentimes unseen conditions such as extreme fog, snow, and rain. And here's a histogram of a 2-month capture period where we drove with a test vehicle through Northern Europe in February. And from the distribution, we can see that our data sets are naturally biased, and such edge cases, such as extremely dense fog in this case, are severely underrepresented, so we cannot just stick to supervision to handle these so-called edge cases. And especially for the very diverse applications, recapturing a data set each time using supervision for another camera or a slightly different camera configuration is a major limitation of today's supervised training approaches. So in this talk, I will argue for computational cameras that provide superhuman vision in these scenarios without supervision. So this will allow us to handle the edge cases not by just adding more data into a supervised training process and letting a downstream network handle the task at hand, but by a co-design of the sensors, the processing pipeline, and the algorithms. This will allow us to handle perception in unseen harsh weather conditions, in low light scenarios. We'll be able to build novel, robust cameras that provide dense depth and imaging in scattering media and at long ranges. And this will allow us to design completely new imaging modalities that, for example, allow us to see objects that are not directly visible, letting a car see around a corner, for example. First, I want to introduce computational cameras that handle the edge cases in conventional camera pipelines. So instead of going out there with a given camera system, capturing more data, using supervised learning to then have a downstream network take care of these edge cases, we can show that by co-designing the ISP, the image processing pipeline, together with the downstream task, we can drastically improve performance for these edge cases. So rather optimize the camera with a given data set to these edge cases, then take a given camera, record more edge cases, and let the neural network take care of it. So here's a typical imaging chain that could be found, for example, in a self-driving vehicle. So here, light from a scene gets focused on the sensor, which requires a raw measurement of it that is then fed into an image processing pipeline, the ISP. These consist of a chain of individual processing blocks with a large set of discrete and continuous hyperparameters. The algorithms themselves are developed by domain experts, oftentimes using heuristics to devise the algorithms, and then also the hyperparameters that affect the performance of said algorithms in each of the camera blocks. So the industry practice is to rely on golden eye experts to manually tune these parameters based on visual inspection and metrics that are based on traditional charts. Then first tune the system, deploy it in the wild, acquire a data set, and fine-tune the models that ingest the images that the ISPs produce. So this process is very time-consuming. It can take months of iterations, and so there's no guarantee that the parameters found as a result of this process are optimal. And for downstream tasks in computer vision, such as object detection or semantic segmentation, there are no golden eye experts that can tell you how to tune the ISPs in an optimal way. So what we did is to rethink this process a little bit and solve it as an optimization problem that automates this process and overcomes this manual design cycle iteration with its many downsides. And by automating this process, we were able to recover parameters for image processing pipeline that accurately recover natural images, tuning for a perceptual loss function in a few hours, ISPs that outperform state-of-the-art low light capture approaches by automatically tuning the processing pipelines, and ISPs that are optimized in an automated fashion for object detection. And so in our approach, the paper is linked here on the right side. We tackle these different imaging applications, and I refer to the paper for those. So I'll talk here about the joint optimization of hardware image processing and downstream detection approaches. So as hardware ISPs are non-differentiable, but highly efficient processing blocks, we need them as hardware to handle the very high throughputs that are needed for modern high-resolution imagers. They are very difficult to integrate with existing first-order optimization methods. So what we do instead of a first-order method that just tunes the parameters directly, we train a proxy network, a differentiable approximation, to the ISP, to the overall processing that is happening from input raw image to a processed output ISP image. So we train this first, and then our proxy network mimics the behavior of the ISP as if we had a real ISP in the loop that based on the parameter settings of said ISP produces a given output image. So we train this by randomly sampling a real hardware ISP producing input-output pairs, so raw input image, and post-processed ISP output pairs, while adjusting the parameters in the random fashion. So we use this then to supervise only the ISP proxy and concatenate that then with a given object detector, for example, a faster RCNNS in this case. And then we can use an RGB to raw method. We can use existing data sets to generate approximate raws that we could have captured with a given sensor system, pipe them into the ISP proxy, which processes the raw images as the hardware ISP would process it. It outputs an RGB image, which is ingested by the network, and then we can place a loss on the output of the detector or other downstream tasks, such as semantic segmentation, for example. And so this allows us then to supervise the parameters of the given hardware ISP, approximated by the differentiable proxy function, in an end-to-end fashion. So we use a very simple modified unit architecture for the proxy that we discard after this process. So this works well for a fixed network architecture. So we can automatically, rather than first going out in the wild and recapturing a full data set, we actually tune the parameters of the ISP towards the particular detector and classification task that we're targeting here. So now, while this approach left the detector fixed, we can also jointly train those. We can jointly, using slightly modified variant, using a proximal optimization method, jointly tune the ISP proxy together with the weights, with the parameters of the downstream network. So this really then tunes the overall, optimizes the overall processing pipeline, including all of the parameters available to us in the hardware ISP, plus all of the weights available to us in a downstream detector for a given task. So here's a qualitative example where, without having Tesla's training data, we were able to outperform the raw detections of a Model S Autopilot stack from last November using the pseudo RAWs that we reverse engineered from a Model S perception system. And you can see here that although we don't have radar, and this is all frame by frame detection, we can do very well and can handle fairly diverse challenging cases using this joint end-to-end approach rather than going out, deploying hundreds of thousands of test vehicles, acquiring large data sets. And here's a further example in an urban scenario, just to give you some more feeling on the results that we can achieve using this joint co-design approach. And here's another example recorded with the onsemi AR231 and evaluated against Nvidia's DriveWorks software, which has been optimized for this particular camera. So you can see that in these super harsh, very difficult conditions where you have a dirty windshield, detections become extremely difficult, especially at low contrast, challenging night conditions, which in general are difficult to handle. But we can see that without having Nvidia's training data that really fuels the performance of their baseline models and DriveWorks, we're able to achieve very good results by this end-to-end optimization approach. And so we have also done some quantitative evaluations in low light and harsh weather scenarios. And to do that, we've acquired a harsh weather data set over about 2 weeks of test drives in North America. Size is about 10,000 frames. And we have compared the traditional sequential approach, that is a traditional ISP with handcrafted expert-tuned parameters, plus a fine-tuned detector on top of it with the joint proposed approach. And what we measured is about 30% improvement in mean average precision for these harsh cases. So here's another example on yet again a different sensor, which shows you the flexibility of the framework. And our approach, in principle, really turns the traditional capture and fine-tune approach on top, where you can use existing post-RGB, post-ISP data, simulate raw data, and use this then to fine-tune your camera system, optimize your camera system, rather than acquiring additional data for fine-tuning and letting the network solve the edge cases that are challenging to handle. So here's another challenging scenario. We find snow particles that are projected into the air by a driving vehicle in front of the capture vehicle. And you can see in the Lidar measurements that there's so much backscatter that you can barely capture any of the actual scene geometry. And our proposed approach can tackle these very challenging scenarios here applied on the camera feed very robustly. So this gives you a hint that potentially such joint optimized approaches may be the solution to overcoming some of the robustness challenges of existing LiDAR-only stacks for autonomous driving applications. Now that we have looked at ways to rethink camera pipelines, next I want to discuss new computational sensors that can deliver dense depth and that are robust to backscatter in snow by using active illumination and computation in a joint fashion. And here you see a multi-sensor feed acquired in harsh weather. What you can observe from the RGB images shown on the left side, which are passive acquisitions, as well as the active pulse LiDAR measurements on the right side, is that both depth acquisition as well as passive imaging, are extremely challenging in such scenarios. Now, let us consider an active time-of-flight imager, which sends out a signal G. So if we only have a direct path, such as the one shown here in blue, then we can calculate the depths by measuring the round-trip time of photons or pulses of photons that travel along this path using the incident signal S on the sensor. However, for realistic scenes, the incoming signal S does not only contain a direct path, but a superposition of delayed and attenuated reflections along direct and indirect path, such as the red one here, reflected off the street surface in this case, or superposed from other scene surfaces, or from scattering particles in the scene, such as the example that we saw at the beginning of the few slides. So S is really the impulse response alpha here, convolved with the illumination signal G. So let's say G is a single pulse. Then S is the same impulse response alpha of the scene. So now by modulating this signal again with a further modulation function F on the sensor, let's say, for example, a narrow gate, we can separate these individual path contributions of the direct and indirect reflections by picking them out as temporal windows. So relying on the convolutional structure of the measurement and discretizing the travel time of light, we're able to formulate the measurements, so the integral of the modulated incoming signal, as a linear transform. So it's a linear transform C, shown here in the bottom right, applied to the unknown temporal impulse response alpha, which is what we want to recover. The transform C contains the different correlation coefficients for different gate pairs if you use narrow gates, and we can invert this linear system in software after the capture. So this inversion becomes easy if C is clearly the canonical basis. So if we use a large number of narrow gates, this becomes straightforward and can perfectly invert this process. However, the canonical basis isn't feasible to implement in practice using conventional CMOS imager. Because we require real-time rates, we have a budget of a few nanosecond gates for an image to enable real-time capture rates. So note that CMOS cameras at a few $100 or very even cheaper at tens of dollars are orders of magnitudes more affordable than a Lidar system, for example. So instead of using a large number of narrow gates, we asked ourselves, can we get away with a few nanosecond gates? With three wide gates as shown here, one ranging from approximately 0 to 70 meters, then another overlapping one from about 20 to 120 meters, and another one from about 60 to 180 meters. So can we, with these overlapping narrow gates, looking at their relative intensities, recover dense depth good enough for us to compete with existing sensors that were able to recover highly accurate dense depth from just 3 wide gating slices, shown here in the top. Result of this process shown on the bottom right, we compare it to a 64-channel LiDAR, a scanning LiDAR, that shows you that you can recover highly accurate but very dense depth from just 3 gates. So how can we recover dense depth from only three gated slices without having any dense depths available to supervise a trained model? So we learn this reconstruction process using a modified but fairly standard encoder-decoder network architecture. And we rely on a few other signals that we can actually use for supervision from other sensors. So we can use sparse labels from scanning LiDAR measurements. We can use adversarial losses trained using synthetic data, which do have dense depths available, but there's a domain gap between the real measured data and the synthetic depth. And we can use gradient priors. So all of this together actually does get us there without having any dense depth for supervision. Here are quantitative evaluations, and we were able to outperform even sparse to dense methods that have access to the sparse scanned LiDAR data. So this really makes the proposed method a viable alternative to scanning LiDAR, achieving very high accuracy across different conditions, including here day and night data acquired in very challenging conditions. And here qualitative results without any temporal post-processing. What we show here particularly is a crop, a narrower region of the scene image at a longer distance. And that shows you that at these very long standoff distances, the high resolution of this particular proposed method for the first time really makes semantic scene understanding tasks at these very long distances possible for the first time. And so the resulting camera is really a novel computational camera that does no longer need brute force temporal sampling as existing scanning LiDAR-based systems do that. And instead, we achieve high spatial resolution and accurate depth, orders of magnitude lower cost than LiDAR systems, and robustness in snow and fog, because we can recover the full temporal impulse response. And can discard pieces of it adequately. At the bottom left, you can see a result in relatively strong backscatter from snow particles, where LiDAR fails completely and gives you an erroneous cloud that you cannot use for adequate detection. In this case, the RGB image, in fact, provides more information. These sensors do not require scanning, which makes them super exciting. And they're very robust in low light. So overall, we think that this really could be a first step towards replacing scanning LiDAR systems as an imaging modality. So the code and the data sets that we use for some of the harsh weather validation and testing, the gated data measured is available. You can see it on the homepage here. There's many other applications that we envision others could use this data set for as well, such as image enhancement in harsh conditions and style transfer. So finally, I would like to introduce computational cameras, a breed of computational cameras that make completely new imaging modalities possible, such as new computational sensors that detect vulnerable road users even if they're not in the direct line of sight of the camera. So superhuman cameras that allow us to see around corners conceptually. Such non-line of sight imaging systems aim at recovering hidden objects. In a scene like this, where here the oncoming vehicle is occluded by the blue truck, and existing approaches have shown that it is possible to image such hidden objects by looking at the indirect reflections of other scene parts that are visible to the camera in this case, such as the road surface in this case here. And they do this by sending out pulses of light onto a visible, diffuse scene surface, shown here in a similar setup in a more of a lab-based scenario. So we send out a pulse into the scene onto a diffuse surface. pulses scanned on the visible wall area. And then we measure the indirect returns from the hidden object on the wall area. So here's such a temporal measurement with picosecond time resolution. And from these temporal measurements, we can recover the hidden object shape and reflectance of this particular hidden object. So in work from last year, we showed that we can rely on specular reflections to outperform methods with picosecond resolution for the same setup geometry. So here's a planar painted road sign from recovered by our method, which was extracted at surprisingly high quality. However, on the right side, you can see that the setup is very restricted. So it's a lab-based setup where the hidden occluder is very close to a diffuse white wall here. And so, in fact, optical methods require instrumentation with severe practical limitations. All optical methods that have been proposed so far, requiring very long acquisition times, excessive cost, and tiny lab-based scenes that only really scale to a few meters at most. So recently we've been able to push this much further and enable long-scale non-line of sight detection and tracking in the wild. And by in the wild, I mean in realistic automotive scenarios at long standoff distances. And here you see our testing vehicle and a number of wall geometries that we can use as relay walls in the wild. And you see here that at least these long distances with a round trip travel distance of around 50 meters, none of the existing methods that have been proposed so far in the optical range have been able to tackle such challenging conditions and scenarios. So to achieve such long ranges, we rely on radio frequency signals. So we send out a signal to a relay wall, where in contrast to optical systems, it likely will be specularly reflected as a result of the long wavelength of RF radiation. As such, most of the walls that are diffused for optical methods preserve energy in the RF regime. We get a diffuse reflection and the specular reflection from the hidden object, and the diffuse reflection back from a hidden object will be reflected back to as shown in this scene here. So while the specular reflection from the third bounce is ignored, the diffuse reflection back to the wall, again another third bounce, is the one that we capture. So we capture specifically the amplitude and Doppler signal of hidden objects that are moving. So unfortunately, these signals are still extremely faint, which is why we have to rely on a joint detection and tracking network to handle these extremely large standoff distances with very faint. So here we see an example measurement, raw measurement on the left side, and its annotated version on the right side, overlaid with the scene geometry at the particular instance when this measurement was taken. And so what we see here is the occluder geometry on the bottom right, as well as a cyclist that is in the direct line of sight of the sensor, and we see a non-line of sight reflection of that very same cyclist, which is reflected off the relay wall. And so we can see here that although we thresholded this carefully just to show what's going on in this particular measurement, that the measurement noise is extremely challenging to handle and makes distinguishing line of sight from non-line of sight objects very challenging. To tackle these noisy measurements, we devise a joint detection and tracking network that relies on raw Doppler and amplitude measurements of a temporal window of n frames. And so for details on this, we revise to the paper, but the key idea behind this particular network is really just to take temporal coherence into account, extract as much temporally coherent data as possible from the raw measurements, fusing the predicted Doppler velocity with the actual object position at a certain time and its next position in time, this next prediction in a joint fashion, trained in an end-to-end way. So here you see some qualitative results, visualized as a bird's eye view on the left side, where we use the white wall in front of us to detect the cyclist even as he moves out of the line of sight. So here's another scene geometry. In this case here we use a building wall as relay wall. See that this pedestrian is tracked adequately. And here we use a sequence of parked cars as relay walls. And you can see here that this new breed, computational imagers, allows you to see much further where conventional line of sight sensors cannot provide any signal anymore. The signal of these indirect reflections is considered to be lost. Here are tracking results for a scene that is visible to the camera. We rotated the camera slightly to make it visible. And the proposed approach achieves on average under 20 centimeters localization accuracy for non-line of sight detections particularly. So in summary, I've introduced computational camera systems that tackle challenging and adverse conditions by a co-design of the camera perception algorithm instead of simply capturing more supervised data to tailor a downstream network towards an existing fixed camera system. Such perceptual cameras can substantially improve the robustness of the imaging and vision stacks of the future. They can allow us to see through fog, see in harsh conditions, see in low light. They can allow very robust perception in these scenarios. They allow us to devise new novel sensors that allow for dense depth, for example, as I've shown. And they can build towards completely new capabilities. For example, they could allow us to detect objects outside the direct line of sight, as I've shown. So really building towards the superhuman vision cameras of tomorrow. And with that, I'd like to thank you.